Even social sciences may play a role for material science, means the availability of materials. As we just spoke about democratization. Can we make a material so cheap that everyone can afford it and that we can give health to everyone? There's a very good example here from IIT where they do 3D printing of bone structures to heal people who had a terrible disease on their bones. And this is kind of democratization. But you need also to know then about biology and medical and the society demands. So it's material science by itself is, I think, a very fascinating topic.
Namaskar and welcome to another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IIT Madras Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global stands for all of the things that India has that need to be visible and usable by the global audience. Come learn more about their efforts in the link in the description below. Material science is at the heart of every new development and technology. And at the heart of material science is a technology that helps us see, understand, and analyze materials. To help us understand this space, which is material science broadly and a subsection of material science which allows us to see inside materials, microscopy of a very different kind. I have a fascinating person, Professor Dr. Stefan Zaefferer, who is the group leader for microscopy and diffraction at the Max Planck Institute for Sustainable Materials. Stefan, welcome to the podcast and thank you for making the time.
Thank you for inviting me. I'm very happy to be here at IIT Madras and to enjoy a 5-week stay here actually, with a lot of interaction and very nice people to meet here. Mm-hmm.
Wonderful.
So happy to
let's start by
give this interview.
Saying that no advancement of humankind has happened without the right material at its heart. So let's talk about what is material science and why should young students today be excited about the future in material science?
That is a very broad question, because as you correctly said, material science is more or less about everything which is in our modern world. And even in the ancient world, material science made many of the things possible. Whether you worked with wood in the very early ages, and you needed to shape this wood, or whether you had bronze or later on iron,
or even the right kind of stone in the Stone Age.
And the right kind of stone, which you were able to shape in the correct way. It was all about materials. But long time it was very much by trial and error. How these materials work and how they actually give their properties and so on. And I would say, since the end of the medieval ages, and maybe here in India also earlier, but I can only speak about the European history as I am familiar with it, people got aware that scientific approach to understand the world and also to understand materials is very important to make them better. And therefore people understood, for example, as our Max Planck Institute was in former times called the Max Planck Institute for Iron Research. And only last year, and it is a 100-year-old institute, and only last year we decided to change a little bit the topic and change to sustainable materials. So, and therefore I mention iron and steel. If you want to optimize this, people knew already that if you have a knife, and you want to make it hard, you have to heat it up and then quench it. But people didn't know what happens in this material when they quench it. And with increasing knowledge about materials, with increasing also microscopy, people understood better what do we need to do and how do we prevent the knife from becoming, from from breaking, for example, and things like that. And knife is only one out of many, many things. Yeah, people developed rubber. People developed, of course, semiconductors. We will come to this, I'm certain. And all kinds of high temperature, low temperature, whatever materials. Everywhere materials play a role. And if I may give one more sentence about modern materials, or modern material science, it is a fascinating technique at the edge of physics, chemistry, and technology. And maybe we come to this later as well. Even social sciences play a role, and medical sciences play a role. They all meet in material science. Yeah. So I find this very fascinating as a scientist, and for the society in a general way.
So you talked of understanding the material and scientifically sort of using it. There are two ways of understanding a material. One is what I would call a top-down, the Hookean view of elasticity. You stress a material, you understand the strain properties. The second is ground up, where you have almost an atomistic view. What does the second view tell a scientist that the first view does not?
Oh, a lot of things, of course. Yeah.
Okay.
I would first say you need both views. Of course, you must first see what are the properties of a material before you try to understand why are they like that.
Okay.
But let's put it like that. Materials get their properties from the interaction of atoms. That's the final reason. Yeah, actually, the most final reason is that electrons are there, and electrons somehow pull on each other or repel each other, and this finally is the reason for all the properties which a material has. That's why people who do density functional theory can claim to be able to calculate all materials' properties, just based on the interaction of metals or of atoms. I'm sorry. And so, if you have a technique which looks at a small scale, it allows you, maybe at the atomic scale or at a slightly higher scale, it allows you to understand the properties and not only to empirically describe them. Yeah, you may find out the Young's modulus, and you may find out that there is a linear relationship between elasticity, between stress and strain, but you may not understand why that is. And why it is in different directions of a material, why it is a different relationship. And this you find only by looking into the atomic structure. Yeah,
wonderful.
And so you are in the microscopy field then.
Perfect. So I mean, you've been sort of embedded in this field of microscopy for several decades now.
Indeed.
Tell us what got you interested in this in the first place. This would have been in the mid-70s? Or
Indeed, yes. Actually, so in the mid-70s, I was about 10 years old.
Okay.
Yeah? And when I was 10 years old, or maybe 12, this journey started. And it started, I find it still fascinating for me. It started with a book which was given to me by my parents.
Okay.
And this book was about electrical devices. So how is an electric motor working? How is a light bulb working? All this. And the last chapter in this book was the electron microscope. And me as a 12-year-old boy, I was really very fascinated. So this is unbelievable. I can see the atoms with it. Already in the 70s, you had atomic resolution, of course, possible. And I was very fascinated about looking on biological samples. So already at school, we did some microscopy with a light microscope, looking on the cell of onions and so on, the famous microscopy. Sure. And I liked that very much. But then I learned, okay, with this microscope, you could see the organelles. You could see how the Golgi apparatus would work and whatever. And I thought, one day I want to do that. And I was 12. Yeah.
Wow.
So and then, okay, I did microscopy and did not follow up the dream to do electron microscopy. But then I started, after my finishing school, a little bit by chance, I didn't get into biology, but into material science. It was a little bit really by chance. Biology would have also been a very preferred part of selection for me. But I got into material science, and the first thing I saw at the university, wow, they have electron microscopes there. And I went to the professor who does this and said, I would love to learn about that. And I was second semester guy. So really very first, maybe third semester, but anyway, very early. And this professor somehow liked me. I don't know, but why. He was one of my roots, I should say. Yeah, Professor Schwarzer at the University of Clausthal-Zellerfeld. And he said, yeah, why don't you do a little job as a Hiwi? I will teach you how this works, and then you can do it. And so I got relatively early, I got into this microscopy on materials. And only then I really learned what is behind that. Yeah, I did something very simple, and more I could advance, and more it fascinated me. And and without being too proud, but it's surprisingly, I'm nowadays in my field worldwide recognized expert in electron microscopy. Yeah, it surprises me myself. It's a boy dream which became true. Yeah.
No, every way there is a lot of hard work and a lot of intellectual output that has gone into making you and setting you where you are.
Oh, if I may,
Yes.
I think I should not forget the famous roots which I have in this. I mentioned my professor. Important is for my career, I had a mother who allowed me to play a lot with everything I wanted. She gave me a chemistry box where I could do experiments in chemistry. I got a physics box where I could make physical experiments. I had a lot of toys at home, which my mother simply said, go and play, I cannot help you more, but I give it to you. And this I should really praise my mother for that. She really helped me getting into this field. It was really important. So then I have put my fundaments now.
So there's a message to all the mothers out there. Help your son become the next professor. You've transitioned from TEM to becoming a pioneer in expanding the use of scanning electron microscopes. Tell us, before we go into that level of detail, tell us what is a modern electron microscope? How does electron microscopy work?
Okay. Once again, this is a very broad question, because there is not only one electron microscope which exists. But let's put it like this. There are two classes of electron microscopes, one which give images, and one class which gives only signals, which you then create into images. And this is important to distinguish, the famous transmission electron microscope, which many people know and which was also in the book which I read, the first example. They work with lenses, like light microscopes, and these lenses create an enlarged image of the electron wave which travels through a sample. So you have a very thin sample of whatever kind of matter. Then electron wave, like a light wave, travels through this sample, interacts with the sample, and creates an image below that sample again. And by a number of lenses, you can magnify this image, and you see really a true image, like in a light microscope, of your sample. This is classical electron microscopy. But many other microscopes are working on a completely different basis. They are having only a very sharply focused beam, and this focused electron beam, creates a signal from the place where it hits the sample. And this place can be as small as a fraction of an atom. Maybe I can later on give a little example how small this is, but anyway, for the moment, so it creates a signal. For example, a secondary electron, or a backscattered electron, or a transmitted electron. And this contains something about this point where the sample has been hit. Can also be X-rays, for example. And now you move your electron beam over the sample from place to place, and at every place you obtain such a signal. You have a detector, or maybe you have 10 detectors around your sample, and everyone detects something else, and then you get actually a lot of measurements, and you take all these measurements and combine them, and then you get, if you want, you get then a picture of your sample by just plotting them next to each other, these pictures. Yeah,
That's the scanning electron.
That's a scanning electron microscope, and you can do this as on a bulk sample or on a transmissive sample. Then you call it scanning transmission electron microscopy. Anyway, these are two very different sorts of microscope. Yeah.
So let's go back and help our audience understand the distinction between light microscopy and electron microscopy. Why did we need electron microscopy? What's lacking in a light microscope?
It's a very nice question. A light microscope, every microscope which works based on waves, let's put it like that, is limited by the wavelengths. The smallest feature you can see, at least in most classical microscopes, is about half of the wavelengths of the radiation which you're using. So if you use light, the smallest wavelengths, the smallest feature you can see is in the order of a few hundred nanometer, maybe 200 nanometer or something like that. And smaller things are simply limited or are simply not possible because of the wavelengths of the light. There's tricks around that, but that's generally it. So if you go to electrons, which are also a form of a wave type, like light, a wave type radiation, you can create much, actually 10,000 times smaller wavelengths than you have it in lights. And that means in principle you can also see 10,000 times smaller things than you have in light. Mm-hmm. And that means you come very easily in the domain where you see atoms, for example. Now, not every technique in electron microscopy can see atoms, because electron microscopes are not as good at light microscopes. They don't have the same accurate lenses. So light lenses made out of glass you can make very accurate, but electron lenses you cannot do so well. So therefore you're not that good in resolution as the wavelengths of electrons would allow, but you're getting to atomic resolution if you want. Yeah. Mm-hmm. So that's the main difference. Yeah, of a wave-based microscopy, let's put it like that.
Sure.
Yeah? Mm-hmm.
Sure. And is there, I'm just going to ask, because I've done a little bit of laser optics. Mm-hmm. Is there a version of a laser microscopy in the material science domain as well? Is that even possible?
Yeah. You can have coherent electron beams in microscopes. Then they also can interfere directly two separate electrons, whatever an electron is. No one really knows what an electron is. But imagine you can create kind of coherent electron sources and they can interfere. But it's a very special sort of microscopy, and I would dare to make large statements about it. I'm not an expert in that. Yeah.
So great. I think that's a good description of the fundamentals of electron microscopy versus light microscopy. Mm-hmm. But life today in the world of material science has gone well beyond all of the basic SEM and TEM. Tell us a little bit about the more advanced techniques like EBSD. And what does EBSD stand for, and why is it a preferred technique for certain measurements?
Okay. So EBSD is, of course, an abbreviation for electron backscatter diffraction. Okay. EBSD, electron backscatter diffraction. And this is a technique which you use in mainly in scanning electron microscopy, which is this form of microscopy where you create a beam and at every place you create a signal. Mm-hmm. Actually, and once again, this is different from TEM where you create an image. So now this EBSD technique is one of the very powerful techniques which is available only for crystalline materials. Okay. Maybe this is not clear. Before I'm talking about the microscopy technique, I should shortly mention that not every material is crystalline, but many materials are crystalline. Yeah. If you take a piece of metal and you look on it, you would say, where is there a crystal? Actually, the piece of metal consists of many usually micrometer large or 10 or 100 micrometer large small crystals, which are glued together with atomic forces, and these crystals determine very much of the properties of the material, all kinds of properties. So EBSD, electron backscatter diffraction, is a technique which is only accessible for crystalline materials. You cannot look on polymers, you cannot look on biological samples, except if it is a tooth or something like that, which is crystalline. You cannot look on glass with this. So we are limited to ceramics, to rocks and minerals, of course to metals and all its variations in the metallic field. That's the technique. That's where the technique works. And so what happens in this EBSD is you place a very fine electron beam onto your sample, and inside of the sample, the electrons travel around in all directions. They get actually scattered by the atoms, and then when they come out again, they feel information given by the crystallographic nature of this lattice, of this crystal, by the very regular arrangement of the atoms. Mm-hmm. And when you then place a detector very close to their sample, you can see this very nice regularity of the crystals in form of a regularity of the electron distribution in space. And here on your screen, you have on the left side, I don't know whether it's visible on one of the cameras, you have such a diffraction pattern, such an electron backscatter diffraction pattern, where all these lines indicate the atomic positions in the crystal.
Okay.
And every crystal is different, so therefore we see for every crystal a different pattern. This one is one from silicon, but in principle you can from any kind of metal and any kind of crystalline matter, you can get such diffraction patterns. And now, these diffraction patterns are very, very, they contain a lot of information on the atomic arrangement. So, for example, they contain information which crystal structure you have there. Is this crystal structure means in which order the atoms are arranged. Yeah, and there's thousands, millions of crystal structures available, and every one of them gives a different diffraction pattern. Yeah, so this we can figure out. We can tell, is it a silicon, is it an iron, is it an aluminium, is it quartz, or whatever you want. Yeah, it's coming out from that. And it contains also information how the atoms which make this crystal structure are standing with respect to the electron beam. We call this orientation. And it contains information how much the atoms are stretched with respect to an unstretched crystal. So we get also the so-called stress in the material, yeah, the residual stress which is in there, and many more things which play a big role in material science can be obtained from just one of these patterns. And now you take such a pattern, then you move to the next point, get another pattern, move to the next point, get another pattern, and you combine all these information together, and then you can create something like what you see there on the right side, a beautiful reconstruction of the crystals inside of a sample based on the analysis of these diffraction patterns. So this is one of the strong techniques of scanning electron microscopy.
Beautiful. How does this distinguish? How is this distinguished from old X-ray diffraction? XRD is still quite widely used as a materials analysis technique. What does this do above an X-ray diffraction?
Yeah, that's actually also a very nice question. I think to a certain extent we have overcome certain features of X-ray diffraction, yeah, with our EBSD technique I will mention in a moment, but we are coming back to X-ray diffraction nowadays. And maybe at the end in the outlook we can talk about that a little bit. X-ray diffraction also doesn't stop in its development. They are able to make smaller and smaller probes. That means smaller and smaller X-ray beams. And this means they come also in the direction of what we can do with EBSD. And they have a couple of advantages even over EBSD. Maybe we'll talk about that later. But for this moment, the classical X-ray diffraction is a technique which looks on relatively large volumes. So usually you look on a number of crystals at the same time.
You're say only an averaged view.
And you see only an average of the crystallographic structure. Yeah? And then you take a so-called Rietveld refinement to calculate out of that details of your crystal structure or of other features of the sample. In EBSD, we don't need this Rietveld refinement because we get from every point a single crystal diffraction pattern, which is able to tell us many things about this local point of the structure. Yeah. So, but it gives us many things which you get also with X-ray diffraction, meaning the phase, meaning the lattice constants, not with the same precision as X-ray, but close to it, and the stresses I mentioned already, and things like that. Yeah. So we are able to. I shouldn't say that so openly, but we are able to replace, to a certain extent, X-ray diffraction with these techniques. Yeah?
Very nice. We started talking about material science. So the ultimate goal of all of these interrogation techniques is to help us either design better materials or understand better materials for the use case in sight. How could I go from this level of information to, let's say, making a better gas turbine blade or a better transistor?
Yeah. One should first say, for this, microscopy alone is not enough.
Okay.
So if you're a good microscopist but you're not a good material scientist, then you will probably not be able to solve that problem. Yeah?
Okay.
So a microscopist should always have a background on the topic what you're working on.
Okay.
Yeah? That means if you're working on biological samples and you don't know how a cell is constructed, you probably will not be able to get the right pictures. And it's the same thing if you do material science and you don't know what are the principles of material science, you will probably look for the wrong features in the material, or you will by chance find it. Yeah. But let's say you have a good understanding of material science, then you can make an amazing amount of progress. And if I take one out of my own experience, and you mentioned high temperatures turbines, which are used in airplanes. Yeah, they are, of course, this is one of the extreme conditions you can put a metal in. Yeah. Let's say an airplane flies over 12 hours from Europe all the way to East Asia. You don't want this to fall down if you're sitting inside, and even if you're not sitting inside. Yeah. One of these important things is that these turbines don't fail.
Yeah.
Yeah, and in these turbines, you have temperatures which range up to, let's say, in the order of 700-800 degrees. And you have a high oxidation pressure because you are putting air in at high temperatures. And you have enormous forces because these 300 tons of airplane all hang on these small blades which are turning around. Yeah? So there's an amazing force on these things. And this over 12 hours at these high temperatures leads to creep and all these things. So you need to understand what is the origin of creep in such a material. And one of the origins is the presence of grain boundaries. Grain boundaries are features where two of these crystals belong together. And they are kind of glued atomically strong together.
In this image, can we say these are grain boundaries?
Everywhere where the color changes, it is a grain boundary.
Okay.
Yeah? This you would not use as a turbine blade because it has too many grain boundaries. Yeah?
Okay.
You would, at best you would have a material which has no grain boundaries at all. We call it a single crystal. That's the same thing in semiconductors. Silicon single crystals are the basic of all electronic devices which we have, or of most of them. But nevertheless, as you make these turbine blades in a technological process, they have grain boundaries. And these grain boundaries are of very small misorientation. The grains change very little bit only. Very difficult to see them. But these techniques which we are developing in microscopy, they see them. And they can tell us how much they contribute to the creep of such a technique, of such a blade. Yeah? And one more example, if you allow.
Sure.
You need to protect this material against oxidation. What we use there is so-called superalloys. They contain nickel and aluminium. That's already nice. Aluminium protects the surface. But if you want to go to higher temperatures, you must have a better protection. Yeah? And therefore, you say, what can we do in order to protect the surface? And one idea is you put a layer of something more oxidation resistant on top. Yeah? And you can do this, for example, by diffusion of certain elements into the surface. And they will create a special film on the surface of this material going into a certain depth and protect from oxidation and even protect from the heat. Yeah? Thermal barrier coatings is one of the names for it. No? And you need to know how well are the atoms fixed to the basic material. Yeah? And do they create any kind of harmful new crystals which are making the blade unuseful or so? All this you can see only with electron microscopy or with high resolution microscopy, let's put it like that. Yeah.
And these techniques can now be applied with the metal under the conditions of stress and temperature that could be potentially, that it could be exposed to?
Sometimes you can do this as well. That's true. You can heat up a sample inside of the microscope to even 800 degrees.
Yeah.
And then look what happens. But most of these processes are slow. Yeah. So a creep process doesn't happen in the 12 hours which the airplane flies from Frankfurt to Tokyo, but it happens if the airplane flies 100 times from Frankfurt to Tokyo. So you can't simulate this easily in a microscope. Okay. So most of these experiments, they are fun to do, but they often, that's a point really, they often don't help very much to understand. Yeah,
that's where good engineering should come in.
Exactly. There you need to you must ask a smart question and then find a way to give a smart answer to that. Yeah, and there you need to be a material scientist and a microscopist, and not just say, I have a microscope, I want to do everything with this microscope.
Okay,
that's important, of course. Yeah,
wonderful. I have a naive question here. All of what you've described seem to be presenting us a two-dimensional view of the material that is exposed to the beam, or in the case of transmission, you said thin layers. What leads us to believe that the three-dimensional structure is what I'm actually measuring?
Yeah. Also, this is an important question indeed. Of course, since many years, people have done sections through materials, and they have also done sections at perpendicular angles so that you see how the material looks from different sides. And already from this, you can conclude how this probably looks in 3 dimensions. Yeah, you can, if you see a feature always looking like a polygon, then it's very likely that also in the dimension which you do not see, it will look like a polygon.
Okay.
Yeah, but sometimes it's important also to see what is exactly the shape of this polygon. I come back to the famous grain boundaries, which I mentioned already, where these crystals are glued together in all materials, by the way. Yeah, it's not only in metals, but in rocks and in ceramics and whatever you have around. These crystals are glued together very severely. And the strength, which is given by these gluing together of crystals, is giving very largely the strength of a material. Yeah. So, and there are boundaries which are not strong and boundaries which are strong. I come to another example in a minute, but you need to know which boundaries do I have there, and what is the statistics. And you do not only need to see, there's a line indicating this polygon, but I want to see how it continues below the surface. So what's the inclination of this? And for this, you can even extend these techniques, as you have it there on your screen, to make 3D microscopy. So you can cut a thin foil or a thin film. Let's put it like that. You remove a thin layer of material, you do this measurement, then you will remove the next thin layer, you do another measurement, and you continue doing like that until you get a 3-dimensional description. And largely this corresponds to what you knew already from two dimensions, but some things you cannot find out by 2 dimensions. That's true.
You've worked both. You worked at Max Planck and in the larger academic ecosystem for a long while, but you also worked with several industry partners. Is microscopy an academic tool, or are there industry applications for this? Why should a company be investing in microscopy of this kind?
This depends very much on the scientific environment you are working in. So that means it depends on the country where you are working, or where you look, on which you look, and on the let's say on the domain of materials which you are interested in. Let's say if you are in Japan, you would find an amazing amount of electron microscopes, even of the highest quality and the highest price as well, in steel industry. Yeah, the Japanese companies value the research, or the academic research or the fundamental research very high. So I was always surprised. I did some years working in Japan. I was surprised how much of high technology microscopy and material science in general they have there in Japan. In Germany, in contrast, the steel industry says, we need maybe 1 microscope, but the rest we let do by a university. We collaborate with a university. They know better than we, no? And they then don't invest very much. And on the other hand, if you're in steel industry, maybe that's the case. But if you're in semiconductor industry, you cannot live without a microscope, even in industry, because you need to see, particularly in failure analysis, or also in the evolution to the next layer, to the next level of integration of an integrated circuit, you need to see these small features. Transistors in electronics are nowadays in the nanometer range, and you can see them only with proper electron microscopy. So in semiconductor industry, you see quite a lot of microscopes, while in steel industry, it is more a rare case. And it depends then, are you in Japan or in Germany or in India or in the United States or wherever? No?
Very nice. So this is not just a tool for research, but there is also use for the electron microscopy bouquet of analysis equipment in the industry context as well.
There is.
Okay. So help us understand what are the kinds of careers that students can look forward to where microscopy meets material science.
So I would always say, don't base your career on being a pure microscopist.
Okay.
That is probably very special and maybe it will give you an academic career path, but I think industry will not very frequently value that very high. Yeah, if you you can do mathematics which never ends if you are in electron microscopy, and not many industries will actually value that. But if you have a good background on microscopy and a good background on materials, then you find, of course, a very valuable field in industry. Let's say I mentioned the steel industry, any kind of materials production industry, even maybe even in parts production, when you make a device, microscopy may play a role. I mentioned semiconductors, but we spoke about super alloys for turbines. Also there, you need to look into these materials and understand what are the chemical gradients and the crystallographic gradients in there. And there, if you know the microscopy well, you certainly have a fantastic tool to study this. Yeah. And one more word, if you just have a very superficial view on the microscopy, then you will not get into the depths of understanding a material. Yeah. You may say, I see a colorful picture as it is there on your screen, but I don't know what these colors mean. Yeah, or I don't know what the grain boundaries which I see there, what this indicates. Why is the material strong or weak? So I need to have both. I need to have a way to understand these pictures, maybe generating them myself, and of course understand what it means for material science. Yeah.
So both a material scientist with knowledge of microscopy can find gainful employment and be a positive contributor in an industry setting as well.
I'm very certain about it, yeah.
Okay. I think, as you said, as we get into, even in India, get into the more technologically advanced disciplines like semiconductors or single crystal turbine blades that are now increasingly being manufactured in India, or at least there's an aspiration and a plan to bring critical technologies into India. Material scientists with knowledge of microscopy will play an important role. Let's say if a young student out there now wants to go learn microscopy, they're convinced by your argument. What's a good starting point, Stefan?
Yeah, that's... What should I say to that? Because this is a little bit depends on, of course, in which area of material science you are. Definitely, you must be in a field where microscopes are available. You must have access to a microscope.
Sure.
You don't learn it only from textbooks.
Okay.
You learn it by doing it.
Okay.
We'll maybe later on come to what you have to learn, what kind of topics you need to study for that. But a textbook alone is definitely not enough.
Okay.
Yeah.
So even before that, a good understanding of physics of materials and a good understanding of basic light or electromagnetic interaction with matter. So this realm of physics needs to be understood by the student, would you say?
Oh yes. So if you come to this topic, definitely what I realized after maybe being 40 years almost in this business, I realized I didn't learn enough mathematics.
Okay.
Yeah. I had a very nice engineering mathematics exposure at the university, but this is not enough for many new fields of material science and of microscopy even more, where in principle you need all the tools which you have in solid state physics. So that means a part of theoretical physics. All this you need to know in order to really feel familiar with all these modern concepts. Yeah, you need to do tensor mathematics and mathematics. You need to be able to solve differential equations, partial differential equations, to be able to really understand what you're doing, particularly when you're doing also development of these techniques, when you want to bring them further. There's lots of mathematics inside. And of course, there's lots of physics inside and lots of chemistry. This needs to be studied and mastered to a certain extent as well. Okay. Physics maybe more than chemistry, although thermodynamics of materials is partly chemistry. I don't know what I should say.
It is.
A very demanding topic and very important to understand. So one must not be afraid of learning difficult things. So it's not something it's not just a colorful image. Microscopy, if you want to really dig down and want to understand it, you need to get familiar with mathematics. That's important. No? And then I mentioned, of course, with physics, chemistry, and the technological background as well. No? How do you deform a material? How do you bake a material or whatever? Also important to know the technology behind it.
So we've talked of microscopy at some length, the different techniques and how it helps a material scientist become a better material scientist.
Yes.
Let's now talk of some emerging trends and new careers in the next 5 to 10 years.
Oh, I see.
Before we go there, there are certain tailwinds that are helping all disciplines of engineering. One of those tailwinds is artificial intelligence. Mm-hmm. Tell us, what is AI doing to material science in general and maybe microscopy in a smaller way?
So, I would say we are still in the beginning of using artificial intelligence in materials.
Okay.
But I see already it has a great perspective. There will be a lot of information coming out of AI, maybe you call it machine learning or big data analysis, which will help us to advance much quicker than we did so far. And one of the things where I see a really big improvement is there is so much knowledge created maybe by microscopy or other techniques over the last 100 years, which is reported in journals and in books and so on. No one can handle all this knowledge by him or herself. And there are tools in AI which allow to look for all the data, and simply finally a computer has a bigger memory than any kind of human, and can also then convolute this knowledge from maybe hundreds or thousands of papers on a certain topic, let's say for thermoelectric materials or steels or aluminium alloys or also any kind of semiconducting materials. They go through the papers, they get the necessary information from these papers and find out what are similarities between these different findings, between these different things, and actually is able to, in principle, find new materials which humans have not found, simply because it can convolute the different properties into one, I don't know how many levels of convolution you need until you find a space where certain properties come out, and then you are able to come to new materials or to new materials behavior also. Yeah? And that is one interesting use where all the existing knowledge will be used, will be actually kind of compiled and convoluted. Another one is, particularly when you are doing microscopy, you're generating, and particularly with these tools which I mentioned, this EBSD, you're generating an amazing amount of data. Yeah, one measurement consists often of 1 million points, and these million points, or even more nowadays, we generate 10 million points in one measurement. Or even when you do 3D microscopy, you can generate 100 million points in one measurement. And they all contain a lot of information about materials. And we do many of these measurements. And now you want to extract from these data what is relevant in these microstructures, for example, in these structures. What kind of defects are in there? material science is a lot about defects in materials, particularly when we talk about crystalline material. So which defects are there and how do they influence the properties? A human often cannot see these fine details because you're overwhelmed by the amount of data which you have there in front of you. So AI is actually able to deal with that. Yeah? Mm. And the last example where I see that is, I showed you, I didn't show you pictures, but we spoke about electron microscopy in TEM or also in scanning electron microscopy, where you see the defects directly, and you may generate thousands of pictures. And these thousands of pictures, no one wants to look for the details in every image. Mm. So we use tools who learn like a human eye or like a human viewer to see, here's a defect, I see it. Yeah, and it's not a crack, it is a crystallographic defect. Or it is a crack and not a crystallographic defect. And a human can see it very nicely, but on thousands of images you get tired and you want to go home. Yeah, so that's why let a machine do it. And I'm currently, very luckily, I'm collaborating with a nice group here at IIT Madras, where we develop tools to find these defects in pictures which we generate at microscopy. And so it's it's machine learning actually. We train a machine to see the things as we see them. Yeah? Mm-hmm. So and this is certainly a very important, let's say, point for the future, that we will use more and more of these electronic tools to actually help us. Yeah, I don't think that they take our work away, but they will make our work progressing quicker. Yeah. Sure. So we are often, medical doctors are afraid that artificial intelligence takes their diagnosis away and then they are out of job. Yeah. That may even be when you look for cancer screening on the skin, probably an AI tool can do that better. Sure. And an AI tool can also look better for the defects. But the AI tool does not know what the defects mean for the material. Yeah. Yeah. And so you can always be a little bit ahead of that as a material scientist and use AI smartly, or machine learning, or all these tools to progress easier. Yeah. Sure. So I see a big development in this direction in AI. Right. Mm.
A second tailwind that all of engineering is experiencing is the drive to be more sustainable. Mm-hmm. And carbon neutral. Mm-hmm. Yes. Where is material science? How is material science feeling that tailwind?
Very much. I think it's one of the big drivers currently of our science. Maybe it has always been, but it was not so well visible. Yeah, and people got crazy and then said, doesn't matter if we make a complete airplane motor out of platinum alloys because it's a little bit more efficient. Let's make it out of platinum. This is, of course, not a good way to do it. No? So, but sustainability was always in the focus, and it becomes more. And you see it, for example. I take my own example. We were Max Planck Institute for Research on Iron and Steels and so on, and we decided to change our name to Max Planck Institute for Sustainable Materials. And one reason is iron and steel is one of the big drivers of carbon dioxide emission. Yes. 10% of all worldwide carbon dioxide emissions is actually created by the steel production. It doesn't matter whether the carbon dioxide is finally responsible really for changing our climate, but it is anyway important to have a sustainable use of our resources. Yeah? If we burn all oil and all coal, maybe it will heat up the atmosphere, but definitely the oil and coal will be gone. That is one important thing. So I have always been in favor, let's find ways to make that in a sustainable way. And sustainable means energy which is coming in will come in from an unlimited resource like the sun.
So you need a circularity to the process.
Yes. And you can do this for steels by using hydrogen, and the hydrogen you have produced from solar energy. Yeah, and what do you need to produce hydrogen from solar energy? You need a solar cell or you need a special reactor which uses the thermal energy of the solar sun to split water into oxygen and hydrogen, and then you get free hydrogen and can use this. So that's one thing, and then you can study how hydrogen can be used to reduce iron ore to iron. But you can also you need also to care. Let's say hydrogen will be the future carrier of energy for our society. But hydrogen is a very detrimental element for many materials. It creeps into every steel, it creeps into every metal, into every material, and weakens it usually. Yeah. So what happens there is an important topic to be studied by material science. Then you think about the other storage of energy. It's electricity, batteries. Battery is really a sustainable way of storing and providing energies, but we are by far not efficient enough. Yeah? You need to understand how do these arrangements of a cathode and an anode and an electrolyte, how do they electrically and microstructurally interact? And how do they degrade over the life of a battery? Yeah, you see your laptop battery after 3 years of use, it has half the capacity as it had before. What happens there inside? It's all material science. It's more material science than we think. Yeah, it's not chemistry only; it's materials. No, and many examples can be given like that. No? You mentioned earlier recycling. Yeah, that's also a very important part of making our world sustainable. You collect all the cars which have been thrown away and you melt a fresh steel out of it. But the problem is, these cars are not created only out of one steel quality, but of several. And they are not only steel, but there's also an electrical motor which is copper, which contains copper. It all goes into the same pot and is molten away. You have suddenly copper in your steel. You don't want that. So how do you deal with that? Yeah, how can you make a new material although it contains copper? We find solutions, and this is all pure material science. Yeah, and this is for many other materials the same way. So sustainability is a very big thing in material science.
Let's talk a little more about the semiconductor industry also.
Okay, right.
I think, as you said, a semiconductor manufacturing industry or even a packaging industry cannot do without electron microscopy. They need that in their core skill. As we go towards increasing compute power with all the GPUs and what role is material science and more specifically microscopy playing there? Are new microscopy techniques specifically becoming required for the semiconductor industry?
There I have to think a little bit. So one big important driver to development of semiconductor industry was the development of atomic resolution transmission electron microscopy.
Okay.
Yeah? So we are getting with our devices, the transistors mainly, yeah, or storage devices, we are getting almost into atomic size structures. Transistors currently have, I think, if I know it well, a diameter of 7 nanometers.
Yeah.
That means you can count the number of atoms which are sitting in these 7 nanometers. It's maybe 20. Yeah. So it's not much across. And finding now how thick needs to be the gate and all the pieces which are in such a conductor, in such a transistor. Do you have the right amount of doping at the right place? Can be only seen when you go to atomic resolution techniques. And one of these atomic resolution techniques is certainly atomic resolution transmission electron microscopy. There is another technique which is well known. It's atom probe tomography. It's a very different sort of microscopy where you count one atom after the other from a very small sample and can reconstruct also the internal elemental, that means chemical composition of a structure at the atomic level. Yeah. So this is certainly this has certainly driven as if the semiconductor industry wouldn't know what it's doing. That means if they could not see inside, they would also not be able to develop it. So there's certainly a driving force coming directly from microscopy. And even the tools which I use, which are at a certain larger level, are very helpful in this regard. We still try to make the interaction volume, that means the resolution, to reduce this, to make a resolution better, to go, for example, you have a large wafer with millions of integrated circuits on this wafer, and you know this little one there is not functioning. What's the reason? Why is it at this place? You want to go there and study this place only. You can't do this with a high-resolution transmission electron microscope directly. So if you would have a tool which can directly look onto it, and a scanning electron microscope could be a tool for that, you would be much quicker and could produce more reliable features and more, maybe, there's all kinds of directions in which you want to develop these tools. So microscopy is certainly a big driver. Which tools are getting their new? I mentioned atom probe tomography is certainly a very important driver to go there, but atom probe tomography also needs to know where it's looking. And for this we have techniques which are called focused ion beam techniques, FIB. They allow, once you know from electron microscopy, from scanning electron microscopy, you know there is the error, then the focused ion beam can cut it out, can cut out a super small sample. On the width of a hair, you can cut thousands of your samples, on the width, not on the length of the hair, and then put them into this atom probe tomography or into high atomic resolution microscopy and look on the detailed defect which you have there. So there's driving in the microscopy area for semiconductor industry.
Let's touch upon another area we've not talked about during this last hour or so, which is biology. We'll briefly,
beautiful.
Your first love, you said, was biology.
Yes, that's it's
What
true.
is electron microscopy doing to biology?
This is a fantastic topic. I'm not an expert, I should say, but I sometimes go to conferences where I, with pleasure, look what the biologists can do, and I sometimes dream if I would have gone in this direction, I would do this right now. That means they can nowadays do transmission electron microscopy, atomic resolution microscopy on proteins. That means you can see, and the main tool for that is cryomicroscopy. Okay. That means you freeze certain structures, you freeze in, and then cut them very thin and observe the proteins which are frozen in there directly, atom by atom in principle. And now, of course, as you can look only through very thin slices, you see these proteins only from a certain projection. And what the people do now is they take projections, so you have a protein of the same kind, multiplied by some funny biological or biochemical technique, and you look on them from all directions, and then you use a computer program to reconstruct how this thing looks in 3D. And then you come to the most amazing images of proteins, how they work in our bodies or in any biological living existence, how they look like, and people have even made progress in seeing how they function. One of the most fascinating talks I have ever seen in this direction was, how does a protein lead to the move of a muscle? By creeping along certain fibers of proteins, some other molecule creeps along and therefore contracts this muscle fiber. Fascinating. This all is transmission electron microscopy. There is such an amazing evolution, particularly, as I mentioned, in cryo-electron microscopy. I cannot follow it, unfortunately. Yes, and you often see that these papers who are published in there, they have hundreds of co-authors, or at least up to 100 co-authors. The author list is as long as the text behind, and this shows that this is very advanced techniques, very complicated. You need someone who makes these proteins, someone who makes and knows how to do that, and someone who makes the samples, of course, and then also the microscopy and the analysis of this microscopy. This is not in one hand. This is too far for it. While in material science, we can still do with relatively small groups. We can still work together.
Sure.
Yeah.
Sure. And what used to be the domain of crystallography in proteins primarily is now becoming more microscopy, isn't it?
Yes. Of course, you can do crystallography in electron microscopy. And this has advantages and disadvantages, or I should not say disadvantages, I should say challenges.
Okay.
Electrons, in contrast to X-ray, interact very heavily with atoms. They have very strong interaction, and this leads to unexpected effects in the diffraction signal. Complicated effects, which you can only understand if you solve complicated equations, more complicated than you do it in X-ray diffraction.
Sure.
And therefore, people have developed what is called diffraction tomography, where you take a protein or let's say a pharmaceutical substance, and you observe it under an electron beam, and then you rotate it slowly in the electron beam, and you obtain diffraction patterns from all these rotations. And from this, together with great computer tools, you are able to reconstruct now from individual microscopically large features of a material, you are able to construct what's the crystal structure, which was done most of the time with X-rays, but when you have only a micrometer large sample, you can't do it easily with X-rays. Yeah? So electron microscopy helps very much in this direction. And we haven't spoken about that also because I'm not an expert there. In pharmaceutical industry, this is quite a common tool nowadays. Yeah.
Very interesting. I mean, clearly this field is ready for both academia and industry, cutting across multiple disciplines. In
Amazing,
the next 5 to 10
yes.
years, what are some ideas you're seeing in material science and microscopy, or both together?
In material science, this is of course almost unforeseeable.
Yeah. You can, right?
But yeah, no, I just pick something which is at my heart, that is the sustainable materials.
Sure.
So improving, for example, the generation of solar fuel from solar light. Yeah, there might be ways. Often it's a question of catalysis, which is a question of materials, that you are storing out of solar energy by splitting up water and then combining it and splitting up carbon dioxide, and combining these two, then you do the same thing as what happens in plants when they do now I'm missing the name. Photosynthesis, yeah. When they do photosynthesis, you can in principle imitate that by materials. And you could create maybe more efficient systems than what the plants have done.
And that is a material science problem.
And that's clearly a material science problem, yes. Of course, chemistry needs to come in. Lots of these functions are chemical reactions, but they happen on surfaces of materials. They need special catalysis on surface to be properly functioning. And often you call a photocatalysis, that means you have material, or photoelectrocatalysis, where you need a material which creates an electric current under the presence of a light and then is able to generate new molecules or something like that. I believe this would be fantastic if we would have this kind of sustainable energy supply. Yeah. There will be more work in this direction, very certainly.
And with microscopy, what are some ideas that you see?
In microscopy, of course, to come back to this particular thing, which I just mentioned, you have more and more in situ microscopy, where you can see processes on a surface or in a material. Really, you can follow it live. You can see a gas comes in, it changes the structure, let's say carbon dioxide, it changes the structure. You can, with spectroscopic methods, you can even see where it bonds, and you can see what kind of gases are created in this way. And you can do this on a very small scale inside of a microscope. That is one thing where I see certainly a big progress. The other progress we spoke about already is artificial intelligence, machine learning approaches, yeah, where you you're able to collect a large amount of data and extract new information which you overlook as a human, maybe. One important thing is you will see more and more software coming in. Yeah, people need to automate microscopy, and this is done either by robotics or it's done by very smart controlling microscopes using language. That means you must be able to script. As a material scientist, you must be able to script and develop robotic processes in material science in order to generate large amounts of data on materials. One point is you have combinatorial materials investigations where you create small sets of samples which all have a little change, and you want to know how this little change leads to properties. So you need to find a way of studying them in an efficient way. And not only study what is the microscopic image, but also what is the property which belongs to it. And then recombine properties and images, or properties and microscopic information. Yeah?
It's almost like you're creating materials in silico inside a computer, experimenting with them before building a material in the lab.
This exists, of course, as well. We have more and more capable tools of calculation. Physicists claim we can calculate any material on our computer and you just cook it up, you material scientists. I have not seen that this really works perfectly. There's always a little thing which is not yet like in nature when you calculate, for example, with quantum mechanical tools. You calculate what's the structure of a material and what's the structure of a defect in this material, but still it is not as exactly as it is in nature. So experiments will not become unnecessary. Yeah, we may propose certain compositions, certain structures on the computer, but it still needs an experimental proof of it.
Maybe a young student listening will improve upon those existing tools.
Absolutely.
Last point, and we were talking about this before we started before we hit the record button. Democratization of electron microscopy. Right? The cheapest microscope out there is, as you said, somewhere near about 100,000 euros.
Yes, let's put it like that.
Okay.
Right.
And you were arguing it doesn't need to be 100,000 euros. It can be more democratically available.
I mentioned to you earlier that you can find a microscope which costs just in quotation marks 30,000 euro. Let's put it like that.
Okay.
And you could build with actually modern detectors. You could probably build a detector which records these electron diffraction patterns we spoke in the beginning, and allow you access to the crystallographic structure at a certain point. And now you can put it onto your kitchen table at home and start measuring the structure of any kind of material if you don't require the highest resolution. If you require a resolution of 1 nanometer, you still have to invest €1 million. Yeah, and if you require a fraction of a nanometer, let's say an angstrom, then you need maybe €10 million. So it's inverse, I think, the resolution. But many materials are living in an area where you are maybe happy with 200 nanometer resolution, and then you could do a kitchen table microscope, which gives you already some nice results. That's a little bit of a dream, of course. It does not yet exist. The kitchen table microscopes exist, but it's still not very democratic because they still cost €50,000. No?
And is there a possibility that smarter software with a reasonable an electron microscope can actually democratize microscopy? The reason I ask is electron microscopy, as old as it is, there are billions of images out there on millions of materials.
Yeah, I mentioned that already.
Yes.
That and maybe I go once in a little detail. I have once followed a beautiful presentation, a beautiful work, which comes out of Japan from the National Institute for Material Science, where they didn't do microscopy, but they just looked into hundreds, thousands of papers. and found out new materials without doing microscopy. By just collecting all the data and then doing a smart algorithm. So they had two smart algorithms. One was finding the papers and finding the information in the papers. And the other one is bringing this together and finding the essence of these data. And then you can do material science even without any microscope. But it's not our topic, of course. Yeah.
Yes.
That's kind of democratization, but still we all know AI is one of the most energy demanding techniques we have on this earth.
Yes.
Yeah.
Yes.
The big computing centers, they create energy which is easily as much as all the airplanes which are flying around the globe.
Yeah.
So whether this is so democratic and so cheap is the second question then, actually. So democratization of material sciences. One point is, the more of these microscopes you create, the cheaper they become, of course.
Yes. Yes.
These very very expensive and complicated microscopes, they are done only in few numbers. And that's also why they are expensive. It's a lot of handwork on them. They use months to be producing one final microscope, and a lot of very dedicated work. So that's why they are expensive. If you would go into mass production, but who wants to have a microscope on the kitchen table? That's a different question.
That sounds like IBM asking who wants to have a PC at home.
Yeah.
Right? There was a question.
Yeah, that's true. Okay, perhaps I'm too critical or too pessimistic. Right.
Stefan, your closing thoughts. We have students watching. Mm-hmm. We want to know what is the most 2 or 3 exciting elements that a young student can look forward to for in a career in microscopy or material science married to microscopy.
I wrote down a few statements which I would like to make. But before these statements, of course, I already during our talk I explained how exciting material science is in general. You are at the edge between several. You are a real interdisciplinary person. You are at the edge between chemistry and physics and technology. And if you are going into medical devices at medicine, you need also to know how a human body functions, yeah? Or what did I say? Even social sciences may play a role for material science, means the availability of materials. As we just spoke about democratization. Can we make a material so cheap that everyone can afford it? And that we can give health to everyone? There's a very good example here from IIT where they do 3D printing of bone structures to heal people who had a terrible disease on their bones. And this is kind of democratization. But you need also to know then about biology and medical and the society demands. So it's material science by itself is, I think, a very fascinating topic. And there is plenty of jobs available. If you now want to combine it with microscopy, it is fascinating for its beauty and for its power of explaining materials. Beauty maybe should be the second point. Power of materials, power of explanation of materials is very obvious, yeah.
Sure.
But it also has a big aesthetic point. It's simply, I like to look into the small world, yeah. And probably I know people who say this is so fascinating what we see there. I want to study more about that. That's one thing. But now let me allow me to make maybe three statements for which I find interesting, and I tell my students when they come into my office, I tell them not at the same time, but I tell them once after the other time. One is sapere aude. Sapere aude. This is a Latin term, and it means be brave enough to think yourself. Don't listen to everything what your professor says is right. Think yourself. Use your own brain to explore. And you have beautiful tools there to do that. No? That's one thing. Yeah, so my second point is coming from a Japanese saying, which you say when you start a meal. And it is saying, itadakimasu. And this means, I am thankful, I'm grateful to everyone who has contributed to this meal. This means the one who has cooked it, The farmer who has grown the plants, or who has grown the animal itself, or the plant itself, and the nature in general who has contributed to this meal. Yeah, and I think we should have the same gratefulness also in science, because we are not alone on the world. We get all these fantastic microscopes, and particularly here in India or in other countries where money is not yet as present as it is maybe in Germany. Many people have contributed money to all these microscopes, which we can use, turn buttons on. Yeah? So we should be grateful that we have these tools, and therefore value these tools also very highly, and be very careful with them, and take the best out of it. I find this is very important. Yeah. So this is itadakimasu. One could say it. I start my microscopy session and I say thank you for everyone who has contributed to these fantastic tools. And the third one is Gambatte kudasai. This is also Japanese. I spent a couple years in Japan, and I got a couple of things which I find is very characteristic for the Japanese lifestyle, and and fits well to science. Gambatte kudasai means work hard and use your resources as much as possible so that you get out what you want to get out. It's a wish, it's a friendly wish. It's not I show you the whip and I beat you. It means I motivate you, work hard, everything is ready for you, you can make it. No? I like this, I often say this to my students, Gambatte kudasai. No? So that's, I find 3 nice statements. And finally, which goes all together with all this, value the nature which is around you. As material scientists, we are kind of masters of materials and also of nature, because we can create all kinds of things, but we must not forget that this is all coming out of nature and all influencing the nature as well. Yeah. I feel this is very important, that we are aware of our natural resources and of our natural origin as well. As humans, we eat from the nature. We cannot eat a silicon chip. We need to eat a potato. And we need not forget that the nature around us is also important. And many phenomena which you see in the nature are coming into finally on our desk as a material science feature, or as a science feature. And we should like nature in order to like our science as well. That's maybe my personal statements about that.
It's a fascinating way to look at the interface of how we live our life and how we do our work.
Yes.
Our work and life are sort of two
coupled. Yes. Right.
They are 2 footpaths lining the same road in some way.
Absolutely. I find this is very important. Yes.
We don't need to make that distinction too hard.
Don't become a science fictionalist. Who is only living in a science fiction room. I think we should not be. That's not our aim, but other people have other opinions about that.
Well, Stefan, this has been a wonderful conversation. I learned many things about how this world of microscopy is changing material science, new techniques coming in to help us develop more sustainable materials and help make technologies more accessible and democratizable to the world at large. Thank you for making the time to come and have this conversation here on this podcast.
Thank you very much. It was a pleasure for me.
Just as it was for me as well.
Good.
That's another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. Until we meet again, be well, do good, and keep in touch. Goodbye.